I would like to introduce an efficient nonlinear manifold reduced pseudo model, which combines the great features of machine learning with the existing numerical discretization methods such as finite element, finite volume, and finite difference in the context of reduced pseudo models. I will start this presentation from purely data-driven black box approach and gradually move toward the conclusion that why we need physics constraints when you ever use a machine learning in data-driven methods. And also, if the time allows, I will introduce a component-wise reduced model, which is especially useful for the problem with distributed high-dimensional parameter space. All right, all the results I'm going to show today is done by Dylan, Kevin, Tony, Yungsoo, David, and Tarek for the first part of the talk. Okay, why reduced pseudo models? I'm sure you guys all are familiar with the reduced models. Just in case there are some folks who are not. You are looking at a beautiful simulation modeled by smooth particle hydrodynamics for shape charge penetration. The simulation is well matched with the experiment, but very expensive. One-fold simulation takes 7.4 days. This is unfortunate in multi-query applications such as design optimization and uncertainty quantification. Therefore, many have tried to build an efficient reduced pseudo model that accelerates their simulations without losing much accuracy. A reduced pseudo model can be built by first considering a parameter space. The parameter space can be initial condition, boundary condition, or material properties, or any parameter, right? Then you collect data, simulation data, by solving full auto model with high performance computing machines for several sample points in your parameter space. Then you apply machine learning techniques to build a reduced pseudo model. And various machine learning techniques are available as listed here. So various reduced pseudo model types are possible, but depending on how much you incorporate physics laws in reduced pseudo models, it can be intrusive or non-intrusive. I will go over some advantages and disadvantages of intrusive and non-intrusive methods in the next slide. But once the reduced pseudo model is built, you can accelerate simulations and predict the solution at various query points here and there, and many more points which you have not used in the training phase. So this is obvious that reduced pseudo model is useful for fast prediction calculation. All right, these reduced pseudo models can be categorized by its level of intrusiveness. For example, black box approach, denoted as BB, is the least intrusive method requiring only data. Then we can think of a more intrusive method, which is the linear subspace reduced model, so-called LS-ROM, where the state fields are represented by a compact linear subspace. And even more intrusive method that is nonlinear manifold reduced model, so-called NM-ROM, where the state fields are represented by a compact nonlinear manifold using the neural network. Roughly speaking, more intrusiveness means more accuracy. So the intrusive reduced pseudo models are more accurate than the black box approach if the same amount of data are used. On the other hand, more intrusiveness means less speed up. So the black box method is faster than the intrusive reduced pseudo models in general. Also, the physics constrained reduced pseudo models are more robust in extrapolation than the black box reduced pseudo models, which will become handy in multi-query applications such as PDE constraint optimization, the design optimization, etc. So let's start with a black box approach. The black box approach I would like to introduce is so-called deep fluid, where nonlinear, the manifold learning algorithm, that is autoencoder, is used for compression and decompression of the solution data W. Here you can imagine, for example, that your solution data are fluid state fields from your flow simulations. In autoencoder, the encoder compresses the input data to a latent space or a reduced dimensional space and decoder decompresses the latent space data to obtain an approximate full state solution. The overall autoencoder parameters are trained by minimizing the difference between the input and approximated data. Once the autoencoder is trained, for the predictions, we apply latent space integrator to propagating time in the latent space. Since the size of the latent space is small, this time integration will be very fast. Then with the predicted latent space solutions, we restore or reconstruct the full state by applying the decoder here. We have applied this black box approach to the 2D Burgers equations, where the simulation is very advection dominated and a shock front is formed and moving, as you can see from the movie. The full order model and deep fluid solutions are very similar in eyeball norm. While the deep fluid gives a speed up of greater than 100 using the latent space dimension of only 5. However, quantitatively, the deep fluid gives the maximum relative error of 38.6%. This might be good enough for animations or digital graphics, but it is a bit too large for scientific application. So for a better accuracy, we need to incorporate the existing first principle or the equation of states in our model. One way of doing this is to use the projection-based reduced pseudo model. To do that, we will start with these governing equations, right? Represented by this ordinary differential equations. Here, W is your state variable, F is the nonlinear function, and T is the time variable, and mu is a parameter. We first approximate the solution as a linear combination of reduced basis phi, right? Whose dimension is, of course, a lot smaller than the full order model dimension big N sub S. Here, the keyword is linear subspace. Then you plug this solution representation into the governing equations. You will end up with an overdetermined system where you have more equations than unknowns. So to close the system, you apply some kind of projection. Here I have applied the Galerkin projection that gives a reduced system of ordinary differential equations. Then you can apply your favorite time integrator to this reduced system. For example, the backward Euler time integrator has been applied here just for the demonstration purpose. And this gives us the fully discretized reduced nonlinear system of equations you have to solve in every time step. By the way, you have to treat this nonlinear term denoted as F properly by applying a hyperreduction, whose term is coined by David here. It's a sampling technique where you sample only the important subset of the nonlinear terms to improve the efficiency. The most famous hyperreduction technique is DEIM, called the discrete empirical interpolation method. The DIM introduces the nonlinear basis phi of F and then express the nonlinear terms as a linear combination of nonlinear basis vectors. Then it introduces a sampling matrix Z, which selects an important subset of the nonlinear term. So after the action of Z on nonlinear term F, only the subset of F will be evaluated. Now the sampling indices of the matrix Z can be obtained through various algorithms. DIM and QDIM are the popular ones. Then the generalized coordinates for nonlinear term F hat can be obtained by solving the interpolation problem, basically. Then you plug this expression into the reduced system of equations wherever the nonlinear term shows up. Then you will end up with these crazy looking equations, but if you look at them close enough, most of the terms can be pre-computed, and this nonlinear term can be efficiently computed thanks to the sampling matrix Z in front of the nonlinear term F. This is how we achieve the efficiency through reduced order model and hyperreduction. There are many variants of DEIM, for example, GNAD, ST-GNAD, and SNS, but the main machinery of the hyperreduction followed this paradigm that I have just introduced here. This traditional linear subspace reduced to the model can be used to accurately accelerate various physical simulations, achieving a speed up of 10 to 1000 with a relative error less than 1% or 5%, for example. So, for example, this linear subspace reduced to the model has been successfully applied to tough simulations such as Lagrangian hydrodynamics. Here you are looking at the cases where the reduced to the model achieves a speed up of 14.6, 22.8, and 31.2, and 87.8 with the accuracy relative error of less than 1% or even less than 0.1%, which implies that the reduced model solution and the full order model solutions are not distinguishable. One great thing about reduced order model, the physics constrained, the data-driven method is that its speed up will increase as we apply it to larger scale problems. Just to see that effect, we have refined the Rayleigh-Taylor instability problems and observe this, the speed up. As you can see from the graph, a higher speed up is achieved as the size of the problem increases. Another great thing about this type of physics constrained reduced to the model is its robustness with extrapolation. Unlike the black box approach, since the reduced to the model directly incorporates the governing equation for the underlying physics, even though it is used to predict the solution for the parameter point away from the training data, it can still give a reasonable accuracy. For example, this graph shows the relative errors of local reduced normal model that is trained at the local point blast energy 0.25 here for the seed of blast simulations. As the prediction point gets away from the training point, the accuracy of the local reduced model deteriorates, but not much though. We still observe that a relative error of less than 1% is maintained around from 0.1 to 0.4, right? This kind of accuracy cannot be achieved by purely data-driven approach because they do not incorporate a physics law. This is the power of the physics constraint model. This has great implication. For example, in gradient-based optimization, let's say you do not have sensitivity informations, and then you can approximate the gradient using the finite difference, right, as written here. Here, if you do each function evaluation, right, at some perturbed point using the extrapolation capability of the local reduced to the model, you can approximate the gradient via finite difference very quickly. Another implication is that you can easily add more local reduced to the models to cover the broader parameter domains. But here the question is how to optimally sample the local reduced to the models in the parameter space. This can be done by the greedy algorithm. The greedy algorithm tries to find a suboptimal, if not optimal, set of a local reduced to the models whose overall accuracy is less than some desirable accuracy level, say, for example, 3%. As a demonstration, we set our parameter space to be blast energy changing from 0.075 to 1.25. As you can see from the movie, both cases have a dramatically different the solution dynamics. The one, it does not hit the boundary, but the other extreme case, it hits the boundary and reflect and interact with the incoming waves. Now, the greedy algorithm starts by setting a desirable the accuracy level. Let's say we want the 30% relative error everywhere. Then build the first local reduced to the model in the middle, for example. Then compute an efficient error indicator on the sampled points over the whole parameter space. Then find out where the error, the maximum error indicator occurs, which is indicated by the red point here. Then we build the local reduced model at that point, right here. And error indicator needs to be updated because the new local ROM has been built there. So we update the error indicator and then find the next maximum relative error which occurs here, and add another local ROM here. And we repeated this process until the overall error indicator is less than the desirable accuracy level. Here is an actual greedy algorithm result. We plot a graph of relative error with respect to the initial blast energy from 0.075 to 1.25. As you can see, the relative error is less than 3% for all the points within the parameter space. This particular greedy algorithm spits out 15 local reduced order models whose location is indicated by blue points here, with actual values listed here. As you can see, the greedy algorithm picks more points for the smaller blast energy here than the large the blast energy. Because the greedy algorithm incorporates the error indicator that is physics informed, physics constraints, it picks these the points suboptimally, if not optimally. If you used, for example, Latin hypercube sampling or tensor product sampling or any random or statistical sampling, you'd not be able to achieve this minimal number of points for the same level of accuracy. So this is the another example showing the power of the physics constrained greedy sampling procedure. Okay, we explained the detailed description of this linear subspace reduced model in this paper, which is published in CMAME. The following, the two softwares are used to generate the numerical results. It is available in open source in GitHub, so that you yourself can grab it and generate these results yourself. As a matter of fact, we have recently launched the webpage for our software LibRAM, where you can find many useful tools and examples regarding physics constraint reduced model for various physical simulations. Additionally, several YouTube videos about reduced models are available if you are not familiar with the physics constraint reduced model. That would be very educationally beneficial. So here are some snippets of LibRAM. The LibRAM is a C++ library for reduced models. It has several features. First, LibRAM can do efficient proper orthogonal decomposition using various singular value decomposition techniques, such as the static SVD, incremental SVD, and randomized SVD, and space-time SVD, etc. Especially the incremental SVD is very powerful if you deal with a large-scale simulation data, and you can build the POD basis as the simulation is running. The LibRAM also has dynamic mode decomposition capability, and if you click example tabs, then you will be able to find several examples for which the dynamic mode decomposition is applied, such as advection problem, Euler equations, heat conductions, and nonlinear elasticity, etc. Okay, the projection-based reduced model examples can be found in the LibRAM webpage also, such as Poisson problem, the nonlinear diffusion problems, and several Lagrangian hydrodynamics problem. Finally, the LibRAM has a greedy algorithm capability that I have just introduced in previous slide. All the source codes are provided, so you can download and try out yourself. Okay. All right. Unfortunately, enough for the LibRAM, the software. Let's go back to the numerical results of the linear subspace reduced model applied to the same 2D Burgers equation. Unfortunately, though, this linear subspace reduced model has a great limitation, that is, it cannot accurately represent a, for example, advection dominated solution with a small basis size. Let's look at the 2D burgers problems, which I have shown you in previous slides in the beginning of the talk. The solution is very advection dominated. As you can see from the movie, LS ROM shows fictitious oscillation in front of the shock wave if the reduced space dimension of 5 is used, resulting in a relative error around 34%, which is not good enough for many scientific applications. So if you think about it, the limitation of the linear subspace reduced model comes from the fact that the solution is represented by a linear combination of the fixed reduced basis. Because the snapshots of these advection dominated problems are linearly independent. So this issue needs to be addressed. As a matter of fact, many researchers and scientists came up with potential solutions for this issue. For example, the shifted POD by Rowley and Reyes, and the registration-based model by Tommaso Tadai, and the Radon transformed the based reduced models and reduced deep network by Donsop Lee, and implicit feature tracking based method by Metjar, and the time windowing ROM for Lagrangian hydrodynamics by Dylan Koblenz. These methods are indeed promising and needs more research efforts, but for the best of my knowledge, these 4 methods are still under development to be extended to fully 3D problems. And this time windowing reduced model requires many windows to handle a long time advection dominated problems. So we focus on the nonlinear manifold reduced model, which first introduced by Gukjin Lee and Kevin Carberg in 2020 from Sandia National Lab, where the linear subspace solution representation is replaced by the nonlinear manifold solution representation. Although they were able to obtain a great accuracy with a small size of latent space, their method was slower than the full order model because the nonlinear manifold reduced order model is adding more nonlinearity to the original governing equations. And the Jacobian computation of the neural network becomes a bottleneck, hindering the fast computation. So today, I'm going to represent a version of nonlinear manifold reduced model that is now a lot faster than the full order model simulation using the hyperreduction and a special structure of the neural network. Okay, to formally explain the nonlinear manifold reduced model, here is the governing equations you have seen before, where W is your solution variable. We approximate the solution with nonlinear manifold, which is represented by the nonlinear function G here. That maps a small latent space dimension to full order model dimension. The nonlinear map is obtained through the autoencoder training with the solution data from the corresponding full order model simulations. Note that the decoder is mapping the latent space to the full order state, so it is perfect for our nonlinear map function G. So we use the decoder as the nonlinear map function. Then we plug this nonlinear manifold solution representation into the governing equation and obtain the overdetermined system where you have more equations than unknowns. Here you must be careful with the nonlinear terms, as I said before. As I emphasize, we need to sample and compute only a subset of the nonlinear terms using the hyperreduction. But when you do the hyperreduction, though, the structure of the neural network matters for efficiency of the nonlinear manifold reduced model. Let's first look at the neural network with the 2 hidden layers as a decoder in the autoencoder. Let's say that the orange, the disks in the output nodes are the selected ones by the sampled matrix Z. You will notice that many hidden nodes are connected. And as you go deeper and deeper in the layer by layer, the number of connected hidden nodes are increasing very fast. This actually degenerates the efficiency of the nonlinear manifold reduced model, especially the Jacobian computation of this neural, the decoder is hindering the fast computation. On the other hand, if you use a shallow neural network that is one hidden layer, then you can easily see that the less number of the hidden nodes are connected to the sampled outputs, which brings us an ultimate efficiency in the nonlinear manifold reducible model after we extract the subnet of chosen nodes. Furthermore, if you sparsify the structure of the neural network, then you will get even better efficiency. So if we apply this nonlinear manifold reduced model to the 2D burgers, shock moving problems you have seen before, then as you can see from all these movies, this nonlinear manifold reduced model is almost identical to the full order model solutions using only latent space dimension of 5. Quantitatively, the NMROM achieves less than 1% maximum relative error. Furthermore, a speed up of 11 is achieved by the NMROM thanks to the hyper reduction techniques we have applied. Okay, this David, do I have time? Maybe 5 or more minutes. If I do, then I can move on
5
to this.
minutes, but
okay.
Yes, you can.
All right.
Continue.
Thank you.
5 minutes.
Okay, great. All right. The second topic I would like to share is a component-wise reduced model lattice design algorithm. This is not particularly a method of handling advection dominated problem, but it is very nice way of overcoming an issue of distributed parameter space, which is very high dimensional, the parameter space. For data-driven methods, having a high dimensional parameter space is really bad because you need to generate lots of simulation data. And for some cases, you cannot even generate those data in your lifetime if the parameter space dimension is so high. For example, the lattice type structure topology optimization problem has exactly that issue in which very high dimensional parameter space needs to be introduced because each design variable is assigned to each finite element. So if you have 1 million finite elements, then you will have 1 million the design variable. Okay, so to accelerate that kind of problem, the lattice structure design optimization process, for example, with good accuracy, we have developed a component-wise reducible model, which was first pioneered by Professor Patera's group at MIT. We have extended it to lattice structure design process. Let me explain the process of the component-wise reducible model in design optimization setting. First of all, we identify the reference components. Here we have identified a simple joint and strut component geometry. Then you introduce finite element discretization for each reference component. Then we build the reducible models for each component, this in component level. And then within the process of building component reducible models, we introduce very important concept called the ports, which is an interface that talks to environments. It connects with other component reducible model. It can be used to impose the boundary conditions. And then it can of course, connect to other component ROMs. It can be used to it can be also used to apply the boundary conditions, and it can be you can rotate the component and attach to the component system, and you do the many more just to complete the desirable the system level the computational domain. Then in design optimizations, we assign a density variable to each component, which varies from 0 to 1. Usually we avoid 0 to ensure the well-posedness. So we set our lower bound to be 0.01. And a small density variable implies putting no material, right? And the density of 1 means you put the material there. We automatize this procedure by solving design optimization, for example, to find an optimal lattice structure minimizing the compliance of the system. So here is a numerical example for lattice structure design using the component-wise reduced model. Here we minimize the compliance, imposing a constraint of the mass being at most 40% of the original the computational domain mass. The downward pressure is applied from the top middle, and the boundary condition is applied on the bottom. As you can see from the movie, the optimization process is depicted by this evolutions. The red is you put the material, and blue means you do not put the material. And as you can see, it forms a optimal the lattice structure. So let's look at how much speed up we can get and accuracy with this component-wise reduced model. For this particular numerical examples, the component-wise reduced model achieves a 660 speedups with respect to the monolithic finite element solve. For accuracy, we easily achieve a relative error of less than 1%. And nice thing about this component-wise reduced model is that the accuracy can be tuned by adding more bases. We observe that the exponential improvement of accuracy as we increase the basis size. And the component-wise reduced model lattice design can be applied for stress constraint problem also. This is considered to be a harder problem than the minimizing compliance problem. Here we introduce 4 different components. Then we define a computational domain whose shape is L bracket, for example, which is a typical stress constraint problem. Then we assemble and fill the computational domain with 4 component reduced to the models, and then delete unnecessary components to find out the optimal L bracket lattice structure. Here is the zoom in picture of components in the optimal design with very detailed stress control plots, which you cannot get with other types of lattice structure design methods. Finally, we can post-process the design to get rid of all the hanging structure to make it pretty and manufacturable. Then we get this smooth and nice lattice design. We have also solved the stress constraint problem for 2D bridge lattice structure design with component-wise reduced to the models. A paper about the stress constraint component-wise reduced model is coming soon, so please stay tuned. And with that, let me conclude the talk with some summary. I hope I have introduced many interesting reduced model techniques, data-driven and physics-constrained approaches. The examples I have shown you include black box approach, deep fluid on 2D Burgers equations, and the linear subspace reduced to the models applied to various Lagrangian hydrodynamics, including seed of blast problem. However, the linear subspace reduced to the model was not able to achieve a good accuracy for long-time advection dominated simulations with small reduced space dimension without special treatment such as time windowing approach. Therefore, we introduced the nonlinear manifold reduced to the model that finally achieves a speed up with a great accuracy with a small latent space dimension. The component-wise reduced model for lattice structure design was also introduced, which accelerates the optimization process considerably, around like 660 times with great accuracy. Finally, I have introduced the web page for Librem, where you will find many useful tools to build data-driven physical simulation models. If you find the things that I have presented today useful for your application, please let me know and let's collaborate. I'm very interested in the collaborations. Okay, with that, let me conclude my talk. Thank you for listening, and any questions are welcome.
Thank you a lot, Yungsoo. If there are questions in the discussion chat, okay. No. So in the room, if there are some questions, I have several, so I can start the discussion. In your greedy algorithm,
yeah.
So you add high fidelity points.
Yeah.
And so it generates local ROM, if I well understand.
Yeah.
So there is maybe a validity domain for each local ROM. And
Right.
how do you design this validity domain locally?
Right. As you can see, if we have only one local ROM, as you can see, the error indicator is the most accurate at that point, and away from that point, the error indicator is increasing. So if you set your target, accuracy level to be 30%, then you decide the neighbor, the trust region of that local ROM to be, any neighbor which achieves the target accuracy less than 30%. So according to this graph, the trust region of this local ROM would be this area. So that is trust region of the local ROM is determined by the error indicator. And we use the residual based error indicator so that we don't have to solve for full order model every time we need to evaluate the error indicator.
Okay, but so this validity domain is set up in the parameter space, if I well understand.
Yes, it is a parameter space. So here 0.075 and 1.25 is the blast and initial blast energy. And those are the parameters we have chosen to demonstrate in this example.
So, yeah, okay. But so here is quite simple because you have only one parameter, but
exactly.
If you have a high dimensional parameter space, do you think it's still okay to get this definition of the validity domain in the parameter space?
Yeah, so if you have the really high dimensional the parameter space and those parameter spaces distributed, then I would recommend to use the component-wise reduced model, which I have been talked about in the later part of the presentation today, which nicely handles the high dimensionality with a local, spatially local ROM, and since the spatially local ROM is small, it can handle, parametric local ROM, spatial ROM can be built locally, and then you can assemble them to take care of the high dimensionality. Yeah, but if it is not the distributed, spatially distributed, it's still challenging. Yeah, the problem is still challenging. Yeah.
I agree. Maybe Fabien, you have a question? No. A last question about the nonlinear ROM. Does your mask depends on the value of the parameter in case of the blast simulation, for instance, or?
Yeah, I do believe so. I mean, the problem we have applied, this the nonlinear manifold reduced model is the 2D Burger's equations with the shock propagations. There we changed the Reynolds number as a parameter, and using those parameter, we were okay with covering all those the variations in that parameter space using the autoencoder with just one mask on the neural network. However, if the parameter space becomes bigger and bigger, then I do believe that yes, that some tailored mask the strategy would be proper.
Yeah, probably yes.
Yes.
Thank you very much. So thank you. Thank you. This is a very nice contribution to nonlinear model reduction.